Adele, yeah, do you pronounce your last name Javan Mart?
Yeah, that's perfect.
Okay. There's nothing French about it.
No.
Okay.
Yeah, we're on YouTube now.
Welcome everybody to our next lecture, which is the IMS Tweedy Award lecture to be given by Adele Javan Mart. The Tweedy Award is named after Richard Tweedy, who was an eminent statistician, and the award was donated by friends and family. I should confess that Richard Tweedy was an academic uncle of mine. So he got his doctorate from the same supervisor, David Kendall, as my supervisor did. And I experienced him as a very kind person and very supportive, in particular to early career researchers. So it's very apt that the IMS Tweedy Award is given to early career researchers. It's a new researcher award for work which was done during the first 5 years after the PhD. And the recipient this year is Adele Javan Mart. He is currently at the USC and University of Southern California, Department of Data Sciences and Operation. He's got also an appointment at the Department of Computer Science. He's obtained a number of awards, such as the NSF Career Award, and a whole list. He obtained his PhD under the supervision of Andrea Montanari at Stanford, and did a postdoc at Stanford and Berkeley. And his undergraduate degree he received from the, to pronounce correctly, from the Sharif University of Technology in Tehran in Iran. And Adele will talk about reliable statistical inference for high dimensional models. Over to you, Adele.
Okay, thank you very much for the introduction. And hi, everyone. I'm Adele Javanmar from University of Southern California, and I'm really honored to present the IMS Tweedy Lecture Award this year. As we all know, Richard Tweedy had a very profound career, and he had both very deep and broad contributions to different topics and domains of statistics, from the convergence analysis of Markov chain to queuing theory to system theory to statistical methods for epidemiology, and the list goes on and on. It's really great pleasure to receive this award in his name. And I would like to thank the award committee for choosing me for the recipient of the award for this year. What I'm gonna present today is on reliable statistical inference for high dimensional models, and it's based on several papers that my colleagues and I finished in the past couple of years. So I would like to start by thanking my collaborators. The first and foremost, Andrea Montanari, my former advisor at Stanford University. Yash Deshpande, who is a postdoc at MIT, and my student Mohammad Mehrabi at the University of Southern California. Okay, to set the stage, we all know that we are living in an era of data deluge, where you can easily collect massive amounts of very fine-grained information very easily on a daily basis. And the eruption that we see in data collection technology has also led to a considerable widespread use of quantitative methods and statistics in different domains, from life sciences to physical sciences to economics, finance, and business applications and e-commerce, where we see that the firms are moving towards deploying machine learning algorithms to improve their revenue, to choose better audience for their product, to come up with better policy for their pricing and advertising, and so on. Maybe the most relevant example to the current pandemic situation is the role of statistics in developing new drugs and vaccinations, where you basically use the statistical analysis to make sure that the drug you're developing would be statistically significant in improving the health of people before providing that into the market at large scale. And I think it's fair to say that the foundations of such widespread use of statistics has been laid down in the previous century by the great work of Ronald Fisher and the other statisticians, who basically contributed significantly to the modern statistics and the experiment design, and somehow operationalize a framework for other researchers in other domains to go about new discoveries. So they talked about the hypothesis testing, and the framework that has been established for doing science was that people come up with some theory, their theory makes some predictions, and then they test the predictions and the data. Based on the outcomes of their experiments, they can analyze whether their theory should be rejected or they fail to reject their theory. But what we know is that the outcomes of the experiments is not always black and white, and it contains a fair amount of uncertainty. And the statistics is basically the language for interpreting and understanding the uncertainty in the outcome of the experiment and to convey the result in an accurate way to the other people. Uncertainty is indispensable, and of course, it's bringing some challenges to the science. Probably the most well-known challenge is the reproducibility. So what do I mean by reproducibility? It means that suppose I have some theory, some method, and I test it on a data set, and I find something interesting, some new discovery. So suppose that my method says, I don't know, a parameter of the model is non-zero, which indicates there is some association between a variable that they have in my model and the response of interest. For instance, I get there is some association between drinking coffee and susceptibility to diabetes. So this is a finding that I have based on the data sets I try my method on. But what I would like is that if someone else take my method and theory, but run it on a different data set, I would like them to also see the same discovery. Not exactly, but up to statistical error. In other words, I would like my result to be reproducible by other researcher teams on other data sets. And this is a natural expectation. We all like the science to be reproducible. We don't want to be the only person who can observe our discoveries. But as we often hear repeatedly, especially in the past decades, the science is becoming less and less reproducible. And we are basically facing an irreproducibility crisis. So here I'm just gathering some of the alarms that we have already in the media and the literature about this crisis. This is a paper that probably most of you have heard about by John Yonindias from Stanford. It has a kind of provocative title and tries to explain in a simple way that what are the most common mistakes that people do in analyzing modern data set, which leads to many, many false discoveries. This is another example from a paper that was published in Science. So what they do in this paper is that they take 100 experiments that were published in the top 3 journals in psychology. And from these 100 experiments, 97 of them reported significant results. So when you look at the individual p-values of these studies, 97 of them have p-value less than 0.05. But in this paper, they try to reproduce the same result for this 100 experiment. And unfortunately, only 36% of the original findings were reproduced by this paper. The other results that were somehow reported to be significant vanished into the air, and they were not reproducible. The other example is this paper that was published in Nature. And this is a study that has been done by Amgen. It's a company based in California. And what they did was that they took 53 studies that were somehow considered to be landmark studies in basic cancer science. And these are the papers that were published in very prestigious, highly accredited journals like Nature, Science, and so on. And they try to reproduce the same result, but only 6 out of these 53, only 11% of them could be replicated by the Amgen. The other discoveries were not reproduced. Again, very relevant to the current situation where FDA is trying to approve some drug or vaccination. You know that there is different phases in developing a drug. And after each phase, your drug the criteria for passing each phase becomes very stringent. So when you get to, let's say, phase 3, it should be almost slam dunk, and you should be very sure that your drug would be effective when you get to this phase of the development process. But in this study, it shows that 22 of the drugs that passed phase 2 were crashed in phase 3. Now you can imagine that if there were some mistake and these drugs were surviving phase 3 and they move until they are delivered to the market, what would be the result, how catastrophic the result would be, and the impact on the people's life. So it's important to control the false discoveries, especially when it has playing an important role on people's lives and their health. So this is the reproducibility crisis, and the media is full of different alarms in different domains that, okay, the results are not reproducible and we should do something about this. And the community has taken some serious actions. There are different research initiatives where you can submit your method, your data set, and they try to see if your method could be reproduced. The result that you have could be reproduced on other settings as well. The other example of the response by the community is that many of the conferences and journals now require the codes and the software to be shared publicly. So somehow help with the culture of reproducibility in the research. And the interesting thing is that we are facing this crisis exactly at the same time that we have a very good technology for collecting data. And the coincidence of these two is not just by chance and can be argued from different perspectives. One argument is that because of the availability of data, the way that people are doing science has shifted from, let's say, 15 or 20 years ago. In 15 or 20 years ago, people were taking mostly a hypothesis-driven approach to science. So they would come up with some theory, they ask some question, formalize a hypothesis, then they collect data and test their hypothesis on the data. And based on the outcome of the experiment, either reject or fail to reject their hypothesis. But now we have data available everywhere. People are constantly playing with data, exploring data to find new patterns and discoveries. And once they get a good insight from the data, then they formalize their hypothesis and proceed with testing their hypothesis. Now, this is completely fine, the data-driven approach to science, as far as you know how to control for different bias and sort of uncertainty in your analysis. As a matter of fact, most people, especially in domains that are not directly related to statistics, don't know how to do this, and that's why you see so many false discoveries. A common mistake, which is very simple to explain, is where people use the same data set both for formulating their hypothesis and also for testing that hypothesis. And you see that there is already an implicit bias here. You also get a similar mistake, of course, in a more subtle way when you have interactive data analysis. Like about the public data set, we know that there are some data sets that are very famous in different domains, and many people are using them to test their methods. But you should also know that when you're testing your method, many other people are also have used the same data set to test their hypothesis. And most of the time, the hypotheses that are formulated are based on the outcome of the previous hypothesis. And there is some implicit bias and correlation among all of these studies. When you're reporting your study to be finding something statistically significant and report the p-value, you should also know that you are one out of many other studies that have been done on the same data set. And if you want to control the overall false discovery rate, you're basically having a multiple hypothesis testing problem. So you cannot just rely on your own study. To control the false discovery rates, of course, you require a central unit, which is lacking in most of the public data set, to somehow control how many studies have been run in this data set. Do you have enough fresh data for the future studies, and whether they can control an overall metric like false discovery rate for all the studies that have been done on this data set. But these are the common things that leads to reproducibility crisis. And as I said, there have been some very good responses by the community, but the questions of interest, of most interest for the statisticians, is that whether we can come up with some new statistical methodology to somehow enhance reproducibility. And this question has initiated many line of interesting research in the past few years. So I've listed some of them that are mostly relevant to this talk. One method is on debiasing method that I will explain during the talk for high dimensional statistical inference. The other one is online control of false discovery rate. So this is when you get in a stream of hypotheses and you want to test this hypothesis, just the time that you get them, but you don't know how many hypotheses you have in total, which could be, of course, infinite. And you don't know what are the future p-values that you're going to get. So the common methods like Benjamin Hodgberg, those wouldn't apply here because they're required to know all the p-values in advance. In online control, you don't have the p-values, you just get them online in a string, but you want to control some of these metrics and criteria like false discovery rate over the infinite horizon. So this is the model that has been proposed to somehow stimulate the type of research and questions that are asked on the public data. The other line of work is on selective inference, the post-selection inference, the adaptive interactive inference, the common cheating and tricks that people do when they are working with data, p-hacking, data snooping, and so on. And I would like to take the opportunity to say there is an interesting workshop that's running online, and it's very easily to follow up the talks. There are many interesting talks on selective inference. It's organized by Rina, Will, Lihua, and Daniel. So if you want to see some of the talks, you can subscribe to their mailing list. And the other line of work is the knockoff framework for controlling the false discovery rate in the high dimensional setting. And the list goes on and on. So there is really a great effort and interesting research going on to somehow improve the reproducibility property of the statistical methods. Okay, so this is the outline for the rest of the talk. I will continue with giving an overall review of debiasing. So that would be the basics of the debiasing techniques for high dimensional models. And then I will explain how you can generalize this method when your data is not IID, which leads to something that we call online debiasing. And then we discuss the application in high dimensional time series. Okay, so let's start with the debiasing technique. I want to continue by a concrete example. Let's say I have n data points. Each data point is a pair of yi, xi. Yi is your response of interest or label, let's say, and xi is the feature vector that you get for the I sample. So the example here is that yi is the glucose level for patient I. It's a real number. And xi is a vector in p dimension that somehow summarizes the medical condition and records and history of each patient. The data that I'm using here is taken from the Kaggle website and it's posted by Practice Fusion Practice Fusion company. So I'm taking just 500 patients from this data set randomly. I look at their medical information and try to come up with around 800 numerical covariates for these people based on the medications that they're taking, the lab result, diagnosis, and so on. So you see that we are already in a high dimensional setting where the number of covariates is larger than the number of samples. And this is very commonplace in modern data analysis. You are measuring too much information for each of your samples. So P is very, very large, and it's even larger than the number of observations, the number of samples N that you have in your data. And the question here is that what are the medical factors that are statistically relevant to my response of interest, to the glucose level? You can ask the same questions in different domains. Like if you are doing genome-wide association studies, you may wonder what are the genes or SNPs that are statistically relevant to my phenotype, like risk of diabetes. Or the other examples, if you are analyzing data for crimes, you might think that what are the factors that are relevant to say whether a criminal would reoffend or not. If you are processing loan applications, for instance, you want to see what are the facts that are statistically significant to deciding whether a loan would be paid off or not. So these are the questions that appear in different domains. And I would like to highlight that these are not prediction problems. Like in the first question, I don't want to predict the glucose level. That's not my primary goal. I can easily measure the glucose level directly from the people. What I would like to address here is to understand what are the fundamental associations between glucose level and other medical records that they have. Okay. Can I say that there is some association between, for instance, drinking coffee and having a high glucose level, and this association is something statistically significant or not? So these are the type of questions that we are interested in, the association between the variables and the response of interest. Now, let's make it more formal. Consider a statistical model. So let's say I have a family of distribution parameterized by vector theta 0 in P dimension, and I don't know what the theta 0 is. So as theta 0 changes, I get different probabilistic model. And then my response of interest is generated based on f of theta 0 condition on the feature xj, xi. And the vector theta 0, you can somehow think that it's encoding the contribution of different variables, different features to the response of interest that they have. So one example is, let's say when I fit a linear model to my data, y is like the glucose level of patients, and x is their feature design. Because I'm living in a high dimensional setting where the number of samples is lower than the number of variables, I need to somehow use some sort of regularization. And the common choice here for linear model is lasso, or try to propose the sparsity penalty and improve the sparsity structure on the solution. So let's say I feed the lasso estimator to this data set. And as you see, most of the entries of the estimated model is 0, as I would expect from the lasso. And some of them are non-zero. And these are sort of the importance of different variables in predicting the response of interest in Y. Okay. So I might say, okay, I can just report the values that are non-zero and say, okay, the corresponding variables are statistically significant maybe. Okay. But the thing is that if I run lasso on a different subpopulation of the data set, so I choose another 500 number of patients from this data set and I refit lasso, I get different estimates. If I choose another subpopulation, again, I get different estimates. So the point estimation that I have would change based on the data set that I'm using. And now the question is whether we can trust, when we see one of the parameters is non-zero, whether we can trust that it's actually non-zero, whether there is some fundamental association between that variable and the response of interest, or was it just because of the specific data set that they have? So the question is that, how do you understand the uncertainty and variations in these estimations, in this point estimation, and move from just having a point estimate to something more ambitious, like some sort of confidence interval, or I can do some hypothesis testing and see whether they are fundamental 0 or non-zero. So this is the main goal formally for doing reliable inference for high dimensional models. I can formalize it, again, using the parlance and the statistics, either through a hypothesis testing problem. So the null hypothesis is that whether the ith coordinate in my model is 0 or not. If it's 0, it means that the ith variable, the ith feature is basically nothing to do with the response of interest. If it's non-zero, it means that there is some important and fundamental association between these two. So I want to test H0i versus its alternative. And these are inference. What I would like to highlight is that these are inference on the single individual parameters of the model. In estimation, we usually care about the overall performance on how good theta hat is over all the coordinates. Like we control the L2 norm of theta hat minus theta. But here I would like to focus on each of the individual parameters and test whether they are 0 or non-zero. Okay? Or I want the other way to formalize it is I want to build valid confidence interval. So given some pre-assigned level alpha, I want to have the coverage 1 minus alpha for each of the individual parameters. So this is what people call doing a statistical inference on low dimensional components of a high dimensional model. So theta is living in a very high dimensional model, but they want to do inference on like low dimensional part of it, like the individual entry, or if I have some functional of theta, like if I use it to do some prediction on new sample, can I build some prediction interval, for instance? So these are the common questions in the high dimensional model. And of course, answering these questions intimately would require to have some good understanding on the distribution characterization of your estimate theta. Now, why is it hard? It seems to be like what people are doing in the statistics. The short answer is the high dimensionality. So if you think about the low dimensional case where you have a fixed number of parameters and the number of samples is going to infinity, you can, for instance, work with the maximum likelihood estimator and then use large sample theory to say that it has some normal distribution. When you go to the high dimensional setting where the number of variables is also growing with the number of samples, first of all, you cannot just go with the maximum likelihood estimator because the number of unknown here is P, the number of parameters that you don't know is P, which is much bigger than the number of observations. So you have more degree of freedom than what you observe, and the maximum likelihood estimator is not well defined. And I need to have some sort of regularization to come up with a well-defined estimator. So let's say I take the minus likelihood and I add some regularization here, and that would be how my estimator is constructed. Like lasso would be one simple example of this. Now, I cannot use the large sample theory to come up with the distribution for theta hat. Like the sort of perturbative argument that people use wouldn't apply here because theta hat minus theta 0 is not negligible. And also most of the time, this regularization would be a non-smooth function. And because of this, you cannot come up with a good distributional characterization of theta. It's notoriously hard. Even in special cases like lasso estimator, characterizing the distribution of theta hat in a general setting for general design metrics is notoriously hard problem. And that's the obstacle in doing a statistical inference for high dimensional models. So what's the idea of debiasing? It basically says that I don't want to work directly with a regular estimator like theta hat. I know that it already has some bias because of the L1 penalty that I'm adding here. The theta that they have is basically encouraged to have low L1 penalty, or if I go with some regularization, I'm pushing somehow theta hat into the region where the regularization is small. So I'm imposing some sort of bias on my estimator already. And characterizing its distribution is also hard, so maybe I can do something else. So what's the idea of debiasing? Let's start with something very simple in the low dimensional setting, where the number of samples is much bigger than the number of variables. And I have a linear model. So in a vector form, y is x times theta 0. X is a n by p matrix. Each row corresponds to one of the samples, and it includes the corresponding feature vector of that sample. Now, in this case, a very simple thing that we can do is ordinary least square. It has explicit form, and I've already written it here. Sigma hat is the empirical covariance. It's x transpose x over n. It's a p by p matrix. I just inverted And then I can construct the least square. Now, what's good about the least square is that if I plug in for y, so y was x theta 0 plus epsilon, and I simplify the term, I get that the least square is theta 0 plus some noise term. So first of all, it's unbiased because the expectation of the second term is 0. And second, I can show that this is Gaussian, right? As far as x is independent of epsilon, and epsilon is coming from some Gaussian or sub-Gaussian distribution, I can use like central limit theorem to show that this goes to a Gaussian distribution. So I have an unbiased estimator whose distribution is completely characterized, and then I can use that to build confidence interval or do hypothesis testing. And the classic things that we have is the length of the confidence interval is scaling with like 1 over square root. Okay, as you get more samples, the length of the intervals would shrink. Okay, so what happens in the high dimensional setting? Whether we can try the same thing. In the high dimensional setting, you are stuck from the first stage because sigma hat is not invertible. So I cannot even define the least square estimator. Sigma hat, again, to recall, was a P by P matrix. It was X transpose X, but the rank is at most N because X was N by P. And when N is smaller than P, when we are in the high dimensional setting, it means that sigma hat is rank deficient and I cannot invert it. So I cannot define the least square estimator. Okay. So we are stuck from the beginning. What can we do? Maybe we can follow the same sort of logic. I don't have sigma hat inverse, but let's say I choose some matrix M, and for the moment you can take your favorite matrix M. We then discuss how to come up with a good choice. And instead of this sigma hat inverse that doesn't exist, I use this matrix M. Okay. So I define a new estimator theta at star based on this matrix M, similar to what we had in the least square. I plug in for y, so y was x theta 0 plus epsilon. I rearrange the terms and I get that theta star is the true model theta 0 plus a bias term plus some Gaussian error. Okay. So you see that theta at star is already biased, which is what you expect because you are trying to learn a high dimensional vector from low dimensional observation. So you would have some bias. Now what you would like is to somehow remove the bias term here. In the low dimensional case, M was just sigma hat inverse and would kill this term completely. But here, sigma hat is not invertible, so I cannot kill M sigma hat minus identity. But how about trying to remove the bias from this estimator? The problem is that the bias depends on theta 0, which is unknown to me. So I cannot remove the bias completely, but maybe instead of theta 0, I can use some estimate of theta 0. So let's say instead of, given that we are in a high dimensional setting, we use lasso estimator instead of theta 0, and somehow try to remove the approximate bias from this estimator, theta at star. So I take theta at star, and then I subtract some good approximation of the bias, where I replace theta 0 by the lasso estimator. Okay. And this is what's called the debias estimator. So let me plug in for theta at star from how I defined it. It was 1 over n mx transpose y in this expression. And then I rearrange the terms and I get to the following expression, which is called the debiasing estimator. So from the high level picture, what we are doing is that you start from the point estimation that you have in high dimension, like the lasso estimator. You know that it has bias, but I'm adding a term to somehow compensate for the bias. And of course, what I get, the theta at d is not sparse anymore. So I'm trying to remove some of the bias and transform them into a variance. So that's the role that I'm trying to do with using the matrix M. Now, if I can do it in a proper way, maybe I can remove the bias from this estimator at the cost of adding some variance to the coordinates of the estimator. But if I can control the variance also in a good rate, maybe I can remove the bias and then get something whose distribution is characterized under the null hypothesis. And if you think about the second term, this is like the one step of the Newton method in optimization. So I start from lasso And then I take one step of the Newton method to the lasso cost function. So I move one step closer to the theta zero. Okay. So this is how the debias estimator is defined. Now the question is, how should I choose matrix M? Okay. And the answer would be in terms of the bias variance decomposition. So if you look at theta at d minus theta zero, it has a bias term and the variance there. And both of these terms depends on the matrix M. So M appears in the bias term, as we see, M sigma minus identity, and also the covariance of the noise term depends on M. So what's a good choice for M? I would like to make the bias as small as possible. Ideally, I want to get rid of the bias. Also, I want to make the variance of the noise as small as possible because the variance here would basically determine the length of the confidence interval, and I want to make them as small as possible. Or if I'm doing the hypothesis testing, the noise that I get here would determine the power of my test. So I want to minimize the noise as well. Okay. So I have two objectives, and I want to make both of them minimum at the same time. So what I can do is that I can form a quadratic optimization problem. The objective would be basically minimizing the maximum variance of the noise coordinate. So if I look at the II coordinate of this quantity here, that would be the variance of the noise, and I want to minimize the maximum variance. So that would be sort of minimizing the maximum length of the confidence interval. At the same time, I want to also control the bias. So if you look at the bias term here, I can control bias by, for instance, using Cauchy-Schwarz, using some dual norm. So that would be M sigma hat minus I, let's say infinity norm, times the L1 norm of the theta zero minus theta. Now, there are many great work on controlling the estimation error of regularized estimator. So I have already good hand on L1 error of lasso. What I would like to control in terms of bias is M sigma minus identity, the infinity norm. Okay, so I put some constraint here. How do I choose this gamma, the threshold for infinity norm? When you're working with a fixed design, this gamma basically depends on some sort of coherence of the design. So the way that we implement it in the code and software is that we do a binary search and basically go for the smallest gamma that makes this optimization problem feasible. If you want to provide the theory and you have some random design, you can see that the optimal choice for this threshold gamma would be something of order square root log p over n. Okay. The other interesting observation about this optimization is that it would decouple over the coordinates I. So I don't need to solve this optimization problem. I can solve it for each of these I separately, which gives each of the optimization would give me one row of the matrix M, and then I stack them together. So this is the overall idea of the debiasing, how you construct the matrix M, and then you plug in this formulation, and you get another estimator that has much less bias compared to the lasso, but of course it has higher noise and it's not sparse anymore. But in terms of a statistical inference, that would be sufficient. So this is the theorem that we get. So I wrote here the theorem for the random design. You have some analogous theorem for the fixed design as well. So what it says is that the debias estimator minus the true model theta zero can be decomposed into a bias and variance term. Distribution of the noise term is completely characterized. It's Gaussian, and you know exactly what the covariance is. So I can do like for my test statistics and do hypothesis testing. I also have a control over the bias term. So the infinity norm of the bias over all the coordinates would be something of order S0 log P over root n. What's S0? S0 is the number of non-zero parameters in the true model, like theta zero. So in the example that we had, like the glucose level and the medical record, maybe I have 800 features, but I wouldn't expect that all of them are relevant to predicting the glucose level. Maybe out of these 800, 20, 30, 50 of them are relevant. So S0 would be the number of relevant features in the actual model. So S0 is basically the L0 norm of theta zero. And this is the bound that I get on the bias. So what I get here is that as far as this one this quantity is going to 0, then the bias is vanishing asymptotically. So what I need is that n should be asymptotically higher than S0 square. So as far as n is growing quadratically in the sparsity, then I can get rid of the bias. And once I have this estimator, I can do the confidence interval, and I get something of order 1 over square root of n. You can argue that the length of the confidence interval that you get here is optimal from different perspectives. From a minimax perspective, it's optimal. If you go to the semi-parametric efficiency, you can also argue that debiasing is optimal in that way as well. And one thing that I want to highlight is that for the people familiar with the literature on lasso and high dimensional inference, the usual assumption like irrepresentability or theta mean condition that are required for support recovery, we don't need them for the debias. You can, for each of these fixed coordinate, you can do a statistical inference without any of these assumptions. Okay. I want to spend a couple slides on the number of samples that you require to have a valid statistical inference method. When we are talking about point estimation and predictions in high dimensional setting, we know that the number of required samples should only grow linearly in terms of sparsity. And that's basically the underlying observation in compressed sensing and high dimensional statistics, where you have many features, you have P features, but as far as n is bigger than the number of non-zero parameters, which you don't know which of them are non-zero, but as far as the number of observation is growing linearly in S0, you can do very good estimation and prediction for your model. For the method of debiasing that I explained here, and also similar approaches in these works, the number of samples that we require should grow quadratically in S0. So you might think that, okay, we are doing something more ambitious. Instead of point estimation, you want to have a confidence interval. And maybe that's why we need like more samples. But the question that's remaining here is whether we can do a statistical inference and confidence interval even under lower sample size. So when n is growing like linearly in S0, can I do something like debiasing? So I have two positive answers for this one that basically says that there's nothing special with this quadratic growth in S0, and maybe you can push it to have some linear requirement, like n bigger than S0 log P should already be enough. So one type of result that we have is for Gaussian design. So here X has IID rows, and each row is coming from some normal distribution with covariance sigma. And we do a sharper analysis of the debiasing approach using a Lib1 technique. And we show that when sigma is known to you, you can already get valid statistical inference as far as n is growing linearly in S0, so this is good. When sigma is unknown, you require some additional constraint, which basically is a lower bound in the number of required samples in terms of S sub omega, which is the sparsity of the precision metrics, the inverse of the population covariance. But let's say you are in the known sigma setting to make things simpler, and it basically says that for Gaussian design, n growing like order of S0 should be enough. Okay. The other positive result that we have is when you are focusing on a more special case where you have standard Gaussian design. So here, the rows are IID and the covariance is identity. Now in this case, we do something based on the approximate message passing machinery and propose some adjustment to the debiasing. So if you recall, the debiasing, the definition here, these coefficients that they have read was already 1. So instead of going 1, we need to do some adjustment, some degrees of freedom adjustment. And we show that if you have this adjustment, you can extend the applicability of this debiasing even to the regime that n, p, and S0 are of the same order. So this is the classical regime that's been considered in compressed sensing. Okay. And we also use the replica method from statistical physics to somehow give non-rigorous argument on why this degree of freedom of adjustment is useful for general Gaussian design. And I would like to highlight the two recent works that was published this year that somehow formalize this analysis for general Gaussian design. Okay, so this is what I wanted to say on the required sample size for debiasing. Now I want to move to the second part of the talk and see how you can extend the statistical inference when you have adaptively collected data. Okay. So the setting that we've been focused on so far was where you have n data points. Each data point was yi, xi, and these data points were IID coming from some common law distribution. You don't need to know the common law distribution of these data, but you assume that they are generated IID. Like the people that I have in my example for glucose level, I assume that okay, the records is coming IID. And this is a common assumption in the statistics and machine learning community for sorts of analyzing and developing theory for methods. But there are many domains of applications where this IID assumption is clearly violated. So I've listed 3 examples here, but again, the list is much broader than this. So the first example is the applications where data is an expensive commodity. Like in clinical trial, it's expensive for me to gather information on different people. So when I'm doing clinical trial, I want to be very cautious about who should be the next sample in my study. And because of that, I look at the previous outcome of my trials, the experiments that I've done, and then I try to choose someone that gives me the most information about my trial. So basically the data points that I'm getting depends on the previous outcome. And because of this, they are not IID anymore. This is an adaptive collection of data. It's sort of an active learning of the model. The other example is in time series. Let's say you are trying to see or predict the stock market. The value of the stocks today would definitely depend on their values on the previous day. And they are not IID. You cannot say that every morning I wake up and these data are generated IID each day. The other example is in the bandit problems, where you have an agent that's interacting with the environment. At each step, the agent takes some action, and based on the action, she gets some reward. Now, this reward somehow gives sort of insight that what should be the next action. The observations that the agent has from the environment are basically the rewards that she gets over time, but the rewards depends on the decision that she made, the action that she takes, and those decisions were based on the previous rewards that she observed. So you see that the observations, the rewards are correlated together through the actions of the agent. And once you look at all of these rewards, you basically have some observations that are correlated to each other, and you want to use these correlated samples to somehow learn the environment. So these are some of the examples where you're dealing with non-IID data. So again, let's make things simple. I focus on linear model. My response yi is linear in terms of the feature vector through some parameter theta 0 that I don't know. And the difference here is that at each point, the feature xi depends on the previous data points. So I choose xi based on my previous I-1 data points. I look at them and then I choose what should be the xi for the next sample. Now, there are 2 natural questions here. The first one is about the consistency. If I have an adaptively collected setting, do I expect that I can learn the model as I get more and more samples? So can I come up with some estimator theta hat that converge ultimately to theta 0 as I get more and more samples? And if you think about each of these settings and try to analyze the common estimator theta hat, you often see that the consistency property is easy to satisfy, and you can get that with the standard estimator. And somewhat expected, because the way that the adaptive data collection setting works is that I want to choose the data, the sample that's most informative about the model. So if I get enough number of samples, I would expect to have enough amount of information about the model, and basically I can come up with a consistent estimator of the model. The second question, though, is a bit subtle. if I have adaptively collected data, can I use them to do validated statistical inference? And now this becomes tricky because the correlation, the adaptation in data collection policy is somehow giving some sort of endogenous dependency about the samples, which brings some bias in my analysis. And we know that bias is a major obstacle for statistical significance. So the question is that if I give you adaptively collected data, can you use this data to come up with statistical significant measures like p-values and confidence intervals? So let's see what happens to the debiasing in this case. Again, to recall, this was the definition of the debiasing, and the matrix M was formed by solving this optimization. So M here, what I would like to highlight is only a function of X. It doesn't depend on Y. So M only depends on sigma hat, which was the empirical covariance of X. It's independent of Y. And what was the argument? We say we have a bias variance decomposition. The bias, we can show it's going to 0 if you choose M proper way. And you have a Gaussian error. Why is this Gaussian? Because M is a function of X, and X is independent of epsilon in a non-adaptive setting, right? So I can use central limit theorem, or if I have Gaussian error, like epsilon is Gaussian, then you can easily say this is Gaussian distribution. But what happens when you have adaptively collected data, even if you can get rid of the first bias term, the second term is also having some sort of bias, because now M depends on X, and in an adaptive setting, your samples are collected based on the previous observation. So X also depends on epsilon. So M, X, both of them are depending and correlated with epsilon. So you cannot say that this is unbiased and Gaussian distribution. So in other words, you have two sources of bias. One is the first term that's basically coming from high dimensionality and regularization in your lasso estimator. The second source of bias is because of the adaptivity in data collection. Now, what can we do? So the idea of online debiasing is that when you're constructing the matrix M, instead of using the entire design X at once, like what we do in this optimization problem here, I want to use the features gradually in an online manner in constructing the matrix M. And somehow I control the correlation between M and epsilon. Okay. So what I do here is that let's focus on the noise term, MX transpose epsilon. So this is the new source of bias. Now, instead of using the same M for all of the samples, I want to use MI for each sample. And I want MI to be measurable with respect to the previous data points that they have so far. Now, if MI is measurable with the history of the data points that they have, it would be independent of epsilon I, because epsilon I is the noise that I'm injecting. It's the exogenous noise at each step. So epsilon I would be independent of the previous history of the data points, of the feature data points. But of course, each of the X would depend on the previous noise. Now, if MI is measurable with respect to this, MI would be independent of epsilon I. And XI would be independent of epsilon I, so I would have a martingale here. And then you can see whether the martingale that you are dealing with is a stable martingale, and if it's stable, then you can use the central limit theorem for the martingale and show that it also has a Gaussian distribution. Okay? So the idea is that instead of working with a fixed matrix M, I want to use different MI for each data point, and MI should be constructed only based on the previous features that they have. Okay? So this is this schematic representation of what we're going to do. We have n data points. I break them into different episodes. How do I choose the length of these episodes? So let's say they are generic, R0, R1, R2. So these are the numbers that would add up to n. And then I can optimize over the length of episode after I characterize what's the bias of my estimator in terms of the length of the episode. Okay, but for now, let's say they are generic. Now, at the end of each episode, I construct a new matrix MI based on the previous data point that they have. So M1 is based on the data points in episode 0, M2 is based on the data points in episode 0 and 1, and so forth. And once I construct MI, I use that to debias the data points that I get in the next episode. Okay? So MI is constructed based on the history, but it's going to be used for future samples. Okay? And this way, I can make sure that the MIs are like measurable with respect to the previous data points, and then the noise term becomes martingale and the argument kicks in. Yeah. So this is the main idea of online debiasing. In the interest of time, I would go to the application to high dimensional time series and do some numerical examples. So in high dimensional time series, there are different models to describe time series. One of the commonly used model is the vector autoregressive. So here you have a vector in p dimensions. So you can think of this vector, for instance, the value of different stocks on different days, or the sales of different products in your company. And you want to see how this vector would evolve over time. And the var d model basically gives you a linear model assumption that ZT is a linear combination of the previous d days of this vector plus some Gaussian nodes. Now the coefficients here are basically matrices, and I want to estimate them. So this is where you want to fit a var d model to your time series data. Now let's say instead of just estimating these matrices AL, I want to also do statistical inference. So I want to test whether, let's say, the ij coordinate of the first matrix is 0 or not. If it's not 0, it means that the value of a stock I today would have something to do with the value of a stock J tomorrow in a statistical significant way. Okay? Or the sales of the product X in my supermarket today would have something to do with the sales of product Y in 5 days from now. And there is some fundamental association between them. So I want to test for this sort of association. Okay? Now, this is an example of adaptive data collection, because the common things that people do in analyzing the var-d model is they stack their observations into matrices in a suitable way to get a linear form, like y equal x theta 0 plus epsilon. But the x that you get is not IID. As you can see, it's basically having some sort of circulant behavior based on the observations that you have. So this is a non-adaptive setting, and we cannot just use the classical debiasing here. So let's do the online debiasing. So if I do the online debiasing, so I skip these, you get something like this one. So this is the numerical example that I'm doing. I'm taking D to be 5. So the lag in my var-d model is 5. I have 15 number of features. P is 15. And I'm looking at 60 data points for this example. And then I want to somehow compute the histogram or the QQ plot of my estimated for these parameters in the model, for these matrices AI. Okay? So the first two plots are the QQ plot and the PP plot. The red curve corresponds to the classical debiasing, and the blue one corresponds to the online debiasing. So you see that the classical debiasing fails to be a Gaussian unbiased estimator, and maybe you can see it from the histogram, or here you see that it's very different, very far from the y equal x-axis in the QQ plot. But if I do online debiasing, so I carefully choose this matrix MI in an online manner to control the dependency in the samples, then I can make it like the blue one, which is a very good approximation to the normal distribution. And once I have the normal distribution for that, I can come up with the test statistics, do the confidence interval, and hypothesis testing. So this somehow says the urgency of developing online debiasing, online version of these methods when you have adaptive setting. You cannot just go with the classical one. And with this, I would like to conclude the talk. Thanks for your attention. If there is any time, I would be happy to take questions.
Well, first of all, in the name of all the participants, thank you very much for a very nice talk. That we do clapping for everybody. Are there
Thank you.
Okay, I have a question regarding your degrees of freedom adjustment.
Mm-hmm. Yeah.
So is that related to classical shrinkage estimators?
Which one, the classical?
That degrees of freedom adjustment. So it looks like a shrinkage adjustment.
Yeah, yeah. So you can basically develop the connection based on like the Shor estimate and sort of the degree of adjustment that people do in the prediction and point estimation as well.
Okay. And there's a moment, Rashi raised his hands. Just have to see. I'll unmute you. Can you ask your question?
Yeah. Hello, Adel. Can you hear me?
Yes.
Yeah.
Thank you very much for your nice talk, and also congratulations for winning this award. I have multiple questions, but I don't know whether Prof. Reinhardt gives me enough time to ask all of them. First of all, why lasso for theta naught? What about for highly correlated situations in which lasso doesn't perform well? That is the first one. Let's go one by one.
Yeah, so that's a very good question. So in some of the adaptive setting, even coming up with a good estimation property for lasso is challenging. The one that they explained here for the time series. So we were fortunate because there were this work by Basu and collaborators from Cornell that analyzed this result, that the estimation error of lasso is analyzed for the time series. But they agree that in more general setting, like the multi-arm bandit problem, it could become challenging even to do the point estimation. But again, for doing the debiasing, the first step is, of course, to have some good consistency property of the lesson.
Is your work also doable for ultra high dimensional case?
Yeah. So this work is for high dimensional case.
No, I'm asking about ultra high dimensional class. You know, whether I'm asking whether it's needed to do, for example, one screening procedure before going to lasso or not. Let's say, for example, short independence screening of a fan or others.
Yeah. So for those cases, we have directly analysis of the lasso. But again, you can also do some screening at the beginning to make the analysis simpler. But for those cases, some of them are discussed in our papers, and we can discuss it more offline. But we have like the analysis of the estimation of error for ultra high dimensional cases.
Yeah,
thank you.
So I think we have to take you up on your offer to discuss offline.
Yeah. I will. Yeah. Thank you. Yeah.
And for just the other audience, if I can be helpful offline. Okay, great. So I stop sharing so the next speaker can.
Thank you.
Okay, sure. Thank you.
So I think we're supposed to go to the next talk now. Greetings, people from Chicago. This is Greg Lawler. It's a great pleasure to introduce Wendelin Berger for the final plenary talk. This is actually one of the few cases where plenary talks are given more than once. So this is the final talk. Of course, I've known Wendelin for many years. Good friend. He has got his degree under direction of Jean-François Legal, University of Paris. Had positions at École Normale Supérieure and a professorship at University of Paris, Orsay, and for many years has been in ETH Zurich. I could list as many awards, and since that seems to be the thing one does at this conference, I think I'll list some. Among his many accomplishments are the Rollo Davidson Prize in 1998, Fermat Prize in 2001, the Lev Prize in 2005, George Polya Prize in 2006, the Heinz Human Prize in 2016, and of course the Fields Medal in mathematics in 2006. He also became a member of the French Academy of Sciences in 2008. He has been one of the leaders in the direction of probability in statistical physics, especially in the use of conformal invariance to prove things, rigorous things that were predicted by physicists. And I think today's talk will be of that form today. So I'm happy to introduce him. And the talk is how to derive the values of some dividing color exponents.
Thank you very much, Greg. So I just want to make sure that you can hear me well before I start. Is that fine?
You'll be heard in Chicago.
Okay, good. So thanks a lot for the introduction. And of course, it's very nice to be introduced by you for a number of reasons, one of which being that it reminds me one of the previous big talks I had to give in front of a fairly unknown audience to me, where you introduced me, and you mentioned some Erdős Bacon numbers and things like that. It's a very, I can just testify that it's a quite strange experience to give the same talk twice in the day, because you know, usually after a talk you sort of can relax, but this time I had to hang on to, you know, try to do stuff, trying to, so I hope I still have enough stamina to go through this talk here. And I also would like to thank the organizers of for the amazing job they did to put on this special symposium that enables all of us to, after all these months of trying to do maths somehow on our own, in our own rooms, to still, you know, be reminded that we are part of a large community. And I can see, I just browsed through some of the many names I know in the audience. And it's a very nice feeling to know you all around. Okay, so the goal of today's lecture, I mean, of course, it's sort of a bit difficult because these sort of plenary lectures supposed to be accessible also to I mean, should be accessible also to non-specialists, and therefore it's always a sort of a tricky exercise to convey some real information and not go into any detail. I'll try to do that as best as I can. The general plan of this talk will be, I'll just present you two of, you know, results that came out of recent joint project that we had and papers that we had with Jason Miller and Scott Sheffield. And I sort of, starting from the statements, I'll try to, you know, hopefully provide you enough motivation to give me an excuse to try to explain to you some of the ideas and concepts that are sort of behind the scenes and that make that one is now able to derive such results that we were not able to prove beforehand. So more specifically, I mean, the talk will have two parts. The first part will be the description of these two percolation type results. And I will sort of give you a bit of conformal loop ensemble background, among other things. And the second part, which will be extremely impressionistic, will try to explain you why Liouville quantum gravity plays a role there. And maybe for those of you who don't know what these things are, I just try to give you some sort of intuition of what a quantum disk is. And also, why in the end all these two-dimensional randomness that we are looking at in this setting is actually very closely related to stable growth fragmentation processes and stable growth fragmentation trees, which are well-known and well-studied objects, you know, sort of more one-dimensional sort of stochastic analysis. Okay, so let's immediately jump into a specific result that is easy to state. And So the idea is you can consider critical bond percolation on the square grid in the upper half plane. So, oops, sorry, I just need. So here it is. So that's just the idea that you have a square grid, and each edge of the square grid is, either kept or erased with probability 1/2, and this you do that independently from each other. Here we are in the upper half plane, meaning that this is the bottom part, and here it's supposed to be sort of infinite all the way up. And so that's the starting points. That's the usual model of critical percolation, Bernoulli critical percolation on the square lattice in the half plane. And so what one is interested usually in percolation is the clusters, the connectivity properties. So here you see you have different islands, and this point is alone, and here you have 3 points in the same island. These are the clusters of critical percolation in 2 dimensions. Now we're going to do something somewhat unusual, which is that we're going to use this percolation setup and as a tool to, give some dependent percolation type coloring of the sites of this model. So what we're going to do is that for each of the clusters, we're going to toss a coin, and with probability 1/2, this cluster will be red, and with probability 1/2, it will be blue, or more generally, we fix a parameter P, and with probability P, a given a cluster will be blue, and with probability 1 minus P, it will be red. So this is what you get. You see it's pretty clear what happened, that some of the clusters became red, some of them became blue, and all the sites that are in the same cluster have the same color. And now we sort of erase the initial information of the percolation. So we just look at the coloring itself of the sites. And now we look at the connectivity properties of the set of blue sites. So this is a way that is sometimes known as divided color model, or comment on that a bit later, to provide you a coloring of the lattice where, of course, the color at the point and the color at another point are correlated positively, meaning that if one point is blue, it sort of increases the chances for another point to be blue, because then if they are in the same cluster, initial percolation cluster, they would have to be blue anyway. And now the question is just look at this from far away, and you ask, take this boundary point, which is the origin, and you look at the probability, you try to see what the probability is that this cluster, blue cluster here, containing the origin. So mind, this is a cluster of clusters, right? So this is a cluster of blue clusters, or blue percolation clusters, whether this has a diameter greater than R or not, right? So what's the probability that this point at the origin is in a blue island that is sort of extremely large, because we're interested in the case where R goes to infinity. So clearly, if you're a little bit into percolation, you would, based on Russo, Sermo, Welsh type ideas, you would immediately say, well, this probability should decay like a power law for a number of reasons. And so it should be R to the power minus A when A is a fixed exponent, depending on P, when R goes to infinity. And so the question is, what is the value of A of P? What is that exponent, right? What sort of that describes the sort of boundary exponent, if you want, because we look at the boundary point and the cluster containing this boundary point. Remember, we're on the upper half plane. What is this one arm boundary exponent of this coloring of percolation clusters? And how does that, what's this number, and how does it depend on P? Now, the answer I'm going to give will be under the assumption that critical percolation is conform invariant in the scaling limit, which is something for the square lattice that everybody believes to be true, but nobody is managing to prove at this point. So if this is true, then we have the following answer, which is this following formula for A in terms of P, which looks a bit daunting. And I would like to take this opportunity to make, a little comment, which is that, all mathematicians are different, and we all have different motivations, and we're excited about different things, possibly in different type of results in mathematics. I myself, I'm not particularly interested in a formula unless this formula actually, tells you, gives you, or builds on some information about the random object itself. This is in some sense a little bit what happens is that, the fact that this formula shows up and has this rather unusual arctangent type feature, this is really unusual for our two-dimensional randomness. That sort of indicates that probably, the way to prove this involves something that is maybe along slightly different lines than for other exponents that people have derived earlier. Okay, so just one little remark is that when p goes to 0, when p is very small, you would expect that the optimal strategy, in order to be, because it's very costly for you to find a blue, that a percolation cluster is blue because p is very, very close to 0, you would expect that the optimal strategy in order for 0 to be in a large blue cluster would be that it is already in a large percolation cluster and that percolation cluster happens to be blue. So when p goes to 0, you would expect that this exponent would converge to the one-arm boundary exponent for critical percolation, which happens to be 1/3, which indeed is the case. Okay. Of course, when p goes to 1, you would expect, then everything is blue, and then you would expect this exponent to go to 0, which is also the case. All right. So just to, give you a slight further motivation, if you do, you are looking in some sense at this model when r goes to infinity in the previous question, which means that it's a little bit like being on, letting the mesh size go to 0 and seeing at the picture from very far away. And so here's basically the similar picture where you do this blue and red coloring of percolation clusters, except that this is on a very fine mesh in the unit disk. And so the question that is asked here is, if I give myself a boundary point on the unit disk, what's the probability that it will belong to one of these big blue clusters here that touches the boundary? So the picture here is a blue cluster touching the boundary is actually drawn. The red clusters touching the boundaries are drawn. The interface between these blue and red clusters are these green curves. And those things that have no color are actually because they are part of clusters that don't touch the boundary. Okay. So, so there are some islands inside, this is an island inside a blue cluster and things like that. Okay. So, so in some sense, the question has to do with whether these, what happens to these green curves and how much do they touch the boundary. That's would be a reformulation of the previous type of question. So this previous result is part of a more general picture, and I don't want to go into details describing to you what FK percolation is, but to start with, indeed, you can try to ask the same question as the one I stated for Bernoulli percolation. When you replace the underlying Bernoulli percolation clusters, but FK percolation clusters. And so that's a particularly dependent percolation model where somehow the edges that had been chosen to be open or closed with probability 1/2 before happen to be positively correlated in a certain way. And the usual way, for those of you who don't know it, I just go through that very quickly, is that to define this critical FK percolation model, what you do is in a finite box, you look at the configuration where edges are open and closed. And for each configuration, you have a number of connected components, a number of faces, and you assign a probability to a given configuration that is going to depend on the configuration. It's proportional to square root of q to the sum of the number of connected components at the number of faces. Number of faces is also more or less the number of connected components of the dual configuration. So this is going to be a self-dual type model. And what you see is that there's a parameter q in the model that tells you, how different somehow you are from percolation, because when q equal 1, you have the usual critical Bernoulli percolation. And when q is greater than 1 here, for instance, then things will become positively correlated. And the system will prefer, right, to have configuration with more connected component and more faces. Okay, so that's the FK percolation model, and it is possible to extend the definition to define these critical FK percolation models in the entire plane or in the upper half plane, always on the square grid, by just letting R go to infinity and this rectangle become larger and larger and larger. Now, if you do ask exactly the same question, you start with an FK percolation cluster model in the upper half plane, you color each cluster, you start with a FK percolation model, you draw, you color each cluster in blue or red with probability P and 1 minus P independently from each other, and you ask the same question about, whether 0 is in a large blue cluster or not. And what we get in the same way is that for each Q smaller or equal to 4, we get some explicit formula for, this exponent that describes this decay rate, this one-arm exponent for these divide and color model. By the way, this coloring of FK percolation clusters has been studied, in the literature. It's sometimes referred to the fuzzy Potts model. I'm going to explain to you why in a moment. And people like Ole Hagström and others have been doing nice work on this. So here I did write down what this exponent A of P is going to be in the case, or should be, under the assumption that we have a conformal invariant scaling limit for the value Q equals to 2, which is the FK percolation model, where basically the parameter of the model is 2, which is important because in fact, in that case, it is known that the FK model has a conformal invariant scaling limit. So in that case, you know that if you start with an FK model for Q equal 2, which is the FK easing model, for a reason I'm going to explain to you that in a moment, what you get is that the exponent that describes this decay of colored FK, one-arm exponent for the colored FK model, takes that form, and that's not that's an unconditional result, because in that case we know that the FK model is conformally invariant in the scaling limit. So you see, it's a somewhat similar form, except that while in the previous case we had a quadratic thing in this quadratic something in this number here. Here you get a quadratic function of this number here. So just two remarks. The first remark is when P equal 1/2, what happens is that if you look at the coloring you obtain for P equal 1/2, and this is why the FK model are interesting models, for Q equal 2, then you get exactly the easing model in the upper half plane, the critical easing model in the upper half plane. That's one of the reasons why the FK percolation models have been introduced before. And therefore, when the exponent is 1/2, you should get, the one-arm exponent, boundary exponent for the easing model. And indeed, it is the case. You can check that. And when P equal to 0, exactly as before, you will get the exponent for the FK model itself, which happens to be here 1/2, which indeed is the case as well. Okay, so I would like to emphasize that these arctangent type things are a bit mysterious. I mean, a bit surprising for at first. The fact that you have exponents where the formula is somehow quadratic, this is a standard feature that you can interpret in various ways. One way would be to say that it is because it has something to do with the quantum gravity feature and the KPZ formula, but these arctangent things is a new type feature. So just a very short few words to say that it is natural to color FK models as explained above, and that if you take an FK model for Q being an integer, and you color independently each cluster of the FK cluster critical FK model into one of the Q available colors. So each cluster takes one of the with 1/Q. Then the obtained coloring is exactly this critical Potts model, which is something which is very easy to define directly, which I'm not going to do. But the important feature of the POTS model that I want to emphasize is that the POTS model can be viewed as being obtained by some just nearest neighbor interaction features. So, a point depend, the way it's correlated to the rest is just via the status of its immediate neighbors. So there's some sort of Markov type spatial Markov property in the POTS model, which happens to be the case where for these P coloring, for this 1/Q coloring of the FK model in Q colors. Now, if instead of coloring in Q colors, you take this P1 minus P coloring, well, then if you take P equals 1/Q, it's the same as just taking Q colors as before and just selecting one. This is blue, and all the others are considered to be non-blue, red. And therefore, sort of these branches in this P1 minus P boundary behavior would have some of these reminiscence of this nearest interaction, neighbor interaction feature. So bottom line is, if you do this P1 minus P coloring in an FK Q model, when P equals 1/Q, something special happens. This coloring has a special feature. All right. So now just a few words about scaling limits, general things. So it is believed that when Q is smaller or equal to 4, the critical FK percolation model will have a continuum scaling limit when the mesh goes to 0 with nice conformal invariance properties. Meaning, so of course, each time I say that, I cannot, I always did, and even more now that he passed away, think of Boris Tsirelson, who always explained to us how important it was that when you look at the scaling limit to explain what you mean, in what sense you take a scaling limit of a model. So here the idea is really that you're looking at the collection of clusters, so you're really only interested in the connectivity properties that you see between blue and red, or between here in particular, between the FK percolation clusters themselves, and that this the scaling limit will then be described by the collection of macroscopic clusters, which will be fractal type objects that you can also describe by the outer and inner boundaries, which will form loops. Right, so a little bit like in the picture you had before, which was, I think, which is here, right? So you're describing the scaling limit via some large islands. So for the FK percolation model, this is believed to be true, and Oded Schramm explained to all of us that if this limit indeed exists in conformal invariant, then the interfaces will have to be SLE type curves, one of his Schramm-Löwen evolutions. Then you can build on that and say that well, the joint law of all the clusters in this FK percolation model could be then defined by these conformal loop ensembles, which for instance Sheffield defined using the sort of SLE branching tree. So in other words, if the scaling limit is conformal invariance on the FK model, then we sort of know what type of scaling limit it has to be. So on the square lattice, which is the model I've been describing, this is only true, has at this point been shown to be the case only for the FK Ising model. This is sort of Smirnov and his collaborators who showed that the limits of the FK Ising interfaces would be one of these SLE kappa prime for kappa prime equals 16/3. And in the limit when Q goes to 0, which happens to be the uniform spanning tree, then with Greg and Oded, we showed that it had to do with SLE8. But for the other models, this is still an open question. So I would like to emphasize one thing, which is that the relation between, if I start with a critical FK percolation model for a given value of Q, which of the SLEs it is that you get in the end is not totally clear. There are various non-rigorous ways to look into predictions in the physics literature to identify them with the features of these SLE models that suggest that Q would be related to kappa prime via this formula here, which has involved the cosine of 4 pi over kappa prime. So indeed, Q will vary between 1 and 4 when kappa prime goes between 4 and 8. Okay, so this is the picture now, that in the scaling limit, you have a picture like that, where with different CLE clusters. So here we haven't decided yet which one is blue and which one is red. And in view of everything, it is therefore a natural thing to look at colorings of CLE kappa prime. So now we are completely on the continuum world, meaning that you have one of these models here. You choose a value, so you have a value kappa prime. You choose P between 0 and 1, and each of the clusters will be colored in blue or red. And then you look at the blue and red clusters of CLE clusters, if you want. So this is, again, then you get a picture like that. In an earlier paper, a couple of years ago, with Jason and Scott, in some sense, what I'm telling you is sort of the end of a cycle of 4 or 5 papers that we wrote together on this subject. So in an earlier paper, what we did was that we showed that for each kappa prime, if you do this coloring procedure, one way to interpret what we said, what we proved there, is that there is one special value, capital Q, such that if you do this, if you choose P equal 1 over Q, so we do this coloring with blue and red with 1 over Q, 1 minus 1 over Q, then something very special happens to the obtained coloring, meaning that it will have a feature that is exactly the continuous analog of the nearest neighbor interaction feature of the Potts model. So in some sense, this says that indeed, these CLE kappa prime coloring, as you might expect, because they are supposed to be the scaling limit of the FK population models, they will have a similar feature. Now, in that paper, so in some sense, this will tell you that the only possible conforming invariant scaling limit of the FK model with Q will be the CLE kappa prime when Q takes this particular value, capital Q. In that paper, we did not establish the general formula for capital Q. Now, using in this recent preprint, using these Liouville quantum gravity ideas, we're able to actually derive this value of capital Q, and we show that indeed it is the one that is anticipated if you look at what I said earlier about what happened in the physics literature, that indeed, if you take a CLE kappa prime, you color with that value of Q, P equals 1 over this, then you have this nearest neighbor interaction model. So in some sense, just out of continuum consideration, you can see that this particular CLE 24 over 5, which is the one that will have to do with capital Q equals 3, would correspond, when you do the coloring into 3 colors, you would get indeed something that is a continuous model with 3 colors and has nearest neighbor interaction features. So I hope this gave you some sort of motivation about why it is sort of useful and interesting to try to work out why the law of these colorings of CLE kappa prime percolation pictures. So the second part of the talk will be trying to give you some notion of some of the ideas that come into the game here. And the goal, right, just to summarize, is you do the CLE kappa prime, you color blue and red, and then you look at the blue-red clusters that you obtain, and then you have these green interfaces between the blue and red clusters here. And the goal is to understand or describe very precisely, this is what we're doing, the law of these green curves. Once we do that, then we are sort of able to deduce this capital Q feature and the value A of P. Okay, so maybe I can, immediately say that show you, a simulation made by Jason. Sorry, it's on the other side. So here on this picture, what you see is instead of working in the disk or in the upper half plane, we're working there in the square. So again, you start, in that case, it's CLE6, because that's the one, of course, that is easier to simulate using critical percolation. So you start with the CLE6, where, clusters, which has clusters, and then you color them in blue and red. And what we showed in the CLE percolation paper, the first one, was that, the left-hand boundary, the top boundary of the collection of blue clusters that are attached to this bottom and right corner of the picture happens to be exactly the same as the right boundary of the red clusters attached to the left-hand side of the boundary. A little bit of work is needed there because of, okay, I'm not going to enter details, but it's not a surprising feature, but it's not an obvious statement. So here the important thing is, okay, I'm not going to, don't want to lose time. And so what I want to explain to you is that in view of the SLE ideas and conformal invariance, and to try to unravel the law of these green type interfaces, the natural thing you want to do is to discover it progressively. So now you're going to start from the bottom left corner, and you are going to draw this interface one off, progressively. And what happens in this movie is that each time you discover a new percolation cluster, you reveal its color, and you draw the entire cluster at once, right? So that's the natural thing to do here in order to have some sort of Markovian property. So here, the green interface has, so you see there are different shades of blue and different shades of red. It's just so that after, at the end, it's just blue and red, but so that at the end you sort of can detect, the different initial percolation clusters behind the scene. So here, this green, at this point, you have discovered this piece of the interface, and you have discovered this, you bounced already on this percolation cluster, so you have drawn it here, and this one, which is red, and you are here. So you see, you have to go through this pocket. The green, at this point, you know already that the green interface will have to go through here, make its way all the way here, and then we'll be living in open space, okay? And what you see, for instance, here is that you have discovered these blue and red ones, and these blue and red ones are creating sort of like these pockets. You know that this green interface will have to go through this pocket, and will have to go through this pocket, etc., and then we'll be able to travel freely. And while you go through these pockets, you're going to have to discover new clusters along the way. Okay, and important feature is, of course, that because of the properties of the FK percolation model, or here percolation, you know that conditionally on this picture that you have here, what is the conditional distribution of what you're going to have there? Well, it's just the coloring of an FK percolation model in that particular domain that you have there. So in some sense, this is reminiscent of Oleg-Schramm's conformal Markov property of SLE, meaning that you have this sort of evolution like this. However, the important feature here, which makes a huge difference with respect to SLE, is that this, when you discover a cluster, you discover the cluster all at once. So these discovery of clusters should play the role of jumps in this exploration, and therefore you're not looking at a usual SLE, but something with jumps. However, the jumps are CLE types loops, because they correspond to clusters, and therefore they are well understood. Okay, so this circle of ideas, leads to the idea that various ideas that sort of, the stationary picture and this exploration of the interface plus adjacent loops is that you are actually exploring a non-connected domain. You have to, go through an infinite chain of domains in front of you first. That's one observation you have to make. And The other thing is that if you use this circle of ideas, you end up with the results of the CLE percolation paper that was saying that, the green, we have a 1 parameter family of possible candidates for the law of this green curve. And in some sense, we know, that there's a 1 parameter family of green curves that are corresponding, each of them define corresponding for each value of P, that is mapped to this 1 parameter family of potential candidates for the green curves. And we know there's a one-to-one mapping, but we don't know what this mapping is. So if you want to describe, the law of the curve or get the exponents, the formula for the exponent, you are basically back to square one, because each green curve will have, each candidate will have its exponents, but you don't know which candidate is associated with which P. So here the trick is to use additional independent Liouville quantum gravity structure on top of CLE. And maybe I use one slide here to just, for those of you who don't know too much about Liouville quantum gravity and not following the amazing flux of very nice papers that come out on this subject these days, I just want to make a very brief summary about the fact that there are, even within this symposium, there have been numerous talks involving Liouville quantum gravity, but sometimes this can mean different approach to Liouville quantum gravity. The general feature of quantum gravity has to do with the idea that you want to define the natural ways in 2 dimensions when you're dealing with quantum gravity in 2 dimensions, to how random metrics or random area measures that you can define in the plane and that are physically meaningful. And there are different approaches to that. One would be, the discrete approach via random planar maps, and numerous French people are involved. I see that I forgot Gilles Schaeffer and all the combinatorial community there. So here, this is an idea where you define a abstract discrete metric space and try to look at the scaling limit. There's the continuum approach via the sort of mating of trees and random geometric objects like SLE processes and using conformal welding that has initiated by Sheffield and have given rise to a number of important papers by Scott with Bertrand and with Jason. And I think you've heard talks involving Liouville quantum gravity in these, in this conference, at least by Gwyn, Holden, and Sun. Now, there's another, even though some of they are also involved in the third approach, which has to do with defining a random metric out of a GFF. And here you have very important recent work by the people mentioned here. And finally, you have a fourth different approach, which has to do with a continuum approach via sort of explicit GFF integral constructions and computations. So you're sort of defining the Liouville measure as acting on some suitable function space. One of the big challenges, of course, is to show that all these, how these different approaches are related to each other. And in some sense, what I'm going to say, the spirit of the present work is to focus on the second approach. So it's very much based on the, mating of trees stories, and to relate it to some features that appear in the discrete setting and in the scaling limit of the discrete setting. So it's sort of building a bridge between the second approach and the first one. That's sort of the idea. And so this discovery of clusters via the percolation, via this green interface that I described to you, is really the continuous counterpart, in some sense, of the peeling algorithm that is the main, devised in the old days by Omer Angel, and also that Schramm was involved and that is sort of at the base of all recent developments on planar maps. For those of you who are interested in that, I recommend you go on Nicolas Curien's webpage and have a look at this lecture notes on peeling of random planar maps, which is Saint-Flour lecture notes. Okay, so now I don't have time, to say much, but very impressionistically, what are we doing here? an LQG structure goes as follows. Now I do it in the sort of bullet point 2 approach. You start with a Gaussian free field, which is this random generalized function defined in the plane, and maybe you are in a domain and you put special boundary conditions, and then you can sort of interpret the exponential of gamma times the Gaussian free field as a nice non-negative generalized function. So the construction of this goes back to Herb Krohn or Jean-Pierre Cahan in the 70s or 80s, which once you define this special natural random function, this in turn defines a random area measure, which is the integral of this function. So a domain for a given domain O, you look at the integral of this generalized function on the domain O, and you declare that's the random area, this area of O, right? So mu is a random area measure. Now, with the well-chosen boundary conditions, you can also make sense of, mu would have some sort of a trace on the boundary that allows you to make sense of the boundary length on the boundary of D that is sort of induced by mu. So these boundary conditions have to do with free boundary conditions, and these are things that are already present in the first papers of Scott in the. Now, what you're looking at is simply connected quantum surface in the sense of Scott is essentially an equivalence class of a domain and an area measure, and then the corresponding boundary length measure. But it's an equivalence under conformal transformation, meaning when you see the quantum surface, you don't know what the domain is. You have no shape of the domain because by Riemann's mapping theorem, all the domains are conformally equivalent. It just tells you, if I give yourself a domain D, how does the area measure, the push forward of the area measure under conformal transformation is in the domain D. Okay, so it's a little bit like you are given Play-Doh with an area measure on the Play-Doh, but it's that you are always allowed to change the shape of the Play-Doh by conformal transformations, and that's what a quantum surface is, right? So you don't know what the shape of the domain is. Now, what Scott also already had in his first quantum zipper paper is when you have such a structure, which is this LQG surface, the random area measure defined out of the Gaussian free field in this way, for this particular special value of gamma related to kappa, then if you draw an independent SLE on top of this domain, it's a very convoluted fractal curve. However, you can make sense of what its length is with respect of the notion of length with respect to this area measure. And the same is true for these SLE kappa prime curves, where kappa prime is 16 over gamma squared. So for each gamma, you have two types of SLE curves that are naturally associated to this, because when you draw them on your Liouville quantum gravity surface, you can define some notion of quantum length of these curves. So in particular, if you are looking at on a CLE kappa prime loop, which is locally looking like an SLE kappa prime, if you draw a CLE kappa prime on top of a LQG surface for the corresponding value of gamma, it will have a length. The inside of this loop will be, a domain which is going to be, made out of simply connected components. Each of these simply connected components will have a boundary length, a finite boundary length. So what you basically are doing is that you are looking at the domain that is inside a CLE kappa prime loop that is defined on the independent LQG surface, and this will be itself, you view this as a quantum surface. Now we go back to our movie here, and we are going to decide that when you discover a loop here, when you discover a CLE loop, you don't see it, right? You are, on your green curve, you are not getting the information about the loop. What you're getting is the information about the quantum surface encircled by the loop. So the story is the following. You have the CLE picture. You have a completely independent LQG structure on it, this random area measure. And now what you do is you follow the green curve and you collect the blue and red quantum surfaces along the way that the green curve is discovering. Now, the important philosophy of what is going on is that this is a point process, right? Sort of each loop that you discover, you know, it's a discrete process. They come in one after the other. And this point process of quantum surfaces that you gather actually happens to be a Poisson point process. So of certain, you know, quantum surface defined under a special measure, which you view as generalized quantum disks. So these quantum disks, in some sense, you know, a posteriori could say, well, it's nothing else than the law of the quantum surface that is encircled typically by a CLE loop, if you want. So here, what you see is that you have a much stronger conformal Markov property, because if you, you know, you just collect this marginal information about these quantum surfaces, you don't see the picture of the exploration. And then what happens is that the law of what remains to be explored will be stationary as well. It will be also a quantum disk with a particular boundary length. And as a result of this, if you look at the evolution, right, of the remaining to be discovered domain, which is a quantum disk with varying boundary length, and if you see what happens from, you know, of the evolution of these boundary lengths, let me just come back to the movie again. Here, you see when the green curve hits the boundary, like it's going about to do now here, you have the choice whether you're going to, you know, which direction you choose. You have to know, you know, where the target point is, which happen, you know, that you go here. Somehow, when the green curve hits the boundary, you're splitting the domain you have to explore into two pieces, and so that would correspond to a negative jump of the boundary length of the to be explored domain. And when you discover a loop, you are actually adding a boundary length to the to be discovered domain, because the loop you're discovering is going to add up to the boundary length. So out of that comes the basically general idea that behind the scene, if you look at this CLE exploration picture, you drawn on a Liouville quantum gravity surface, you get variants of stable growth fragmentation process and trees that are objects that have been actually analyzed and developed for other reasons. The reason, of course, that these processes show up is that they are very natural, because they satisfy some independence properties and some scaling variance properties, and therefore show up in a number of cases. It is nice here that sort of you get this sort of incarnation of these stable growth fragmentation trees in the two-dimensional picture here. So what happens here is that you have this growth fragmentation tree associated to a stable growth fragmentation tree that is defined in this way, that has to do with the, you know, jumps, positive, negative jumps of the boundary length. And actually the whole tree will encode exactly the joint information of both the CLE and the independent LQG structure that is on top of it. So you have sort of this bijection picture of growth fragmentation tree. Stable growth fragmentation tree contains all basically the same information as the LQG surface, but also how it is actually drawn in the plane, how you have to embed it in the plane. Okay, so now, how does this help us to identify the law depending on P? Well, then you can use various tricks, because one just, you know, background result that is sort of behind the scene, that is enabling us to compute A of P and identify the law of the subordinate of this fragmentation process, is the following classical result in stable processes. Namely, if you take an asymmetric stable process of index alpha smaller than 1, so it's a one-dimensional asymmetric stable process of alpha smaller than 1, so it's the difference between U times a subordinator of index alpha minus a subordinator of index alpha, both being independent. Then if you look at the running maximum of this process, it's not difficult to see that this will have to be a stable subordinator itself. And the value of the index of this subordinator, this index beta, can be explicitly determined in terms of alpha and u. So the simple formula involving ratios of sinuses. Now, in particular, if you know alpha and beta, then you can recover what the asymmetry parameter is, what is the ratio between the positive jumps and the negative jumps of the subordinator. Now, this is exactly the type of formula we are using here to identify, the law of the process in terms of P. And here I'm cutting corners in a very brutal way, but you can say the P is telling you how many of these jumps are on the right and how many of these jumps are on the left so it is a little bit like a ratio of jumps, and that's somehow what happens. So this tangent or arctangent type formula comes in there is the same one as the one that shows up in that type of formula between one-dimensional stable processes. So I don't have time to explain you exactly what the trick is, for instance, to interpret the range of the stable subordinator in terms of our exploration process, and I mean the range of the running maximum or running infimum of the stable subordinators. But there's a simple picture type explanation that one can use. And I'll skip this. And I think that's time for me to conclude. I just list here the references, which are the preprints relevant to what I've just said. But of course, they build on also the earlier things which have to do with the construction of conformal loop ensemble on the one hand, ideas coming from imaginary geometry papers developed by Jason and Scott, and this for this last bit, this paper and this paper here, the mating of tree type ideas. So these are all sort of papers with Jason and Scott. I would like to thank you all for your attention, and also because that's what one is supposed to do if we are the last plenary speaker of the last, in a big conference, is to thank the organizers. So I hope Leif and Andreas and Siva and are listening. So I, on behalf of everyone, would like to thank you very much for making this conference possible. And I'm sure it has played a very positive impact, not only mathematically, but also for all our common well-being of reminding us that we are part of a nice and thriving community. And I would like to thank you very much for all the amazing efforts you put in to organize this in such short notice. Thank you.
Thank you very much. We're starting to get some questions. I'm going to do some unmuting. Get this. I'm going to start by unmuting you and Gwen.
Yep.
Yeah, so I just wanted to ask, so when you were talking about the exponent for the size of the cluster in percolation at the beginning, I was just wondering if you can actually get that exponent rigorously in the case of site percolation on the triangular lattice, because that's like the one case to actually know that that it has a conformally invariant limit.
Yes, I mean the reason I did not, I chose this, bond percolation on the square lattice because I wanted to move on to the FK percolation, and also because then you have to be a bit careful about how you color the clusters and what you do with the little holes in between. But essentially, you could cook up a model for starting for triangular on the triangular critical triangular percolation of the triangular lattice percolation, and then color those clusters in an appropriate way and making sense of what you call, how you define the clusters of clusters. But you have to, and everything works, but you have to be a bit careful about how to define it. It's a bit less natural than the usual coloring of, bond percolation type models where you get the coloring of the sites. It's sort of a bit easier to explain. So, but yes, you can do that. And of course, the one arm, I mean, yeah, that's also the case where we know things at scaling limits.
All right.
I'm now going to call on Richard Gill.
Okay, thank you. Thank you, Greg. Great talk. I put a question in the chat. Actually, it's been answered by somebody called Titus Lupu.
Yes.
My question was, are these quantum constructions performed after a weak rotation? So the space-time we're looking at is not the real space-time, but the space-time found after replacing T by IT. And Titus Lupu says that it is.
Yeah, I mean, in some sense, yes. I mean,
Okay, in a mathematical sense, that's what you do, isn't it? Or what they do,
yeah,
or not?
I mean, that's where, the actual origin of, these are sort of Euclidean conformal field theories, which, have been introduced precisely,
Yeah.
Motivated by the quantum thing and then taking this rotation. I mean, the answer would be very long, but I mean, the first thing is that everything Titus always says and always writes is clever, and he's always right. And the second thing is that, and the second thing is that there is actually a number of recent papers having to do with imaginary chaos, where a number of where somehow these exponential of I times the Gaussian free field comes back through the window here, and
Yeah.
so there are nice recent developments.
Yes, I know. They're very important recent developments. I'm just trying to clarify it in my mind, and I fight with physicists about Bell's inequalities and.
Yeah. However, I should say that this particular work is really, as soon as we look for the geometric, I mean, is still quite Euclidean, right? I don't claim that I would understand how to do this coloring of CLE percolation clusters and these type of things when, whether this is actually relevant when you go back with imaginary things.
I'm going to take the opportunity just to ask a technical question, just in terms of the quantum gravity measure on boundaries or SLE curves or SLE boundary curves.
Mm-hmm.
I mean, there's a natural way of doing it, which is to basically follow LQG area measure, but to use Minkowski content measure.
Mm-hmm.
And that's not too hard to justify, but is that the same object or a different object?
That's a very good question. I think one has to be very careful. I mean, this what happens in the way you get this, the SLE curve is very windy, and the way this boundary length sort of pops out has to do with this quantum, the imaginary geometry type, invariance. So the idea is that if you uniformize the domain that is drawn, the boundary of the curve, if you do if you uniformize it, then the conformal transformation, has a phi, will turn a lot. So you will have phi prime terms that show up. And so my answer is probably the answer is yes, but one has to be careful. And if you give me a couple of hours to try to prove it, I might to give you a rigorous full proof, I might fail. But somebody like Wayne or others might actually know that this has been done somewhere or not. But yeah, I mean, the general idea is still that, you're looking, when you define these boundary lengths, you have some sort of information about the, the area, the quantum area of the neighborhood. However, one has to be careful, what neighborhood we are sort of talking about. So I think a little bit of care is needed there.
Okay, so at this point, I think, I don't think I'm going to unmute everybody. So Benjamin is just going to have to understand that all of us are about to clap for you. You'll hear a few of us, but let's all thank Benjamin for this excellent talk. they did get unmuted. Okay. And now I turn the podium to Siva Atreya.
Thank you. Thank you, Greg. Thanks, Mentalin, as well. Just a small sort of closing of thoughts for the meeting before we sort of end this session. I just begin by saying that John Christoph, Andreas, Christian, and myself were part of the organizing committee, but we stayed safe in the committee part of the organizing committee. It was live from start to finish. No issue with that, I think. And also, if you notice the program, Life had an opening, but no closing. And I think that's Life's true philosophy. There's no closing of this effort, I think. It's going to go on forever, I think. It's no closing of it. So maybe Life can summarize his thoughts for the meeting.
Okay, very quickly, let me summarize. So that's the end of a short but rather intense sprint of 8 weeks. So since all this was started in the middle of the COVID time, everything had to go rather quickly. I would like to thank to many people who contributed. I even need a list because there were so many. Thanks to the plenary speakers, thanks to all the authors of these about 100 posters, thanks to the 600 participants who took the challenge to produce a 10 minutes video, which we are all not used to do, but they all managed wonderfully. Thanks to the moderators of about 120 live discussions, which I really liked to see, and I went in many of them. Most of them were really nice. Thanks to the 23 session chairs, which we recruited on a very, well, within a week. So all of them were rather brave to take the challenge of something we all didn't know where it goes. Thanks to all these senior members of the community that accepted to try this Ask Me Anything sessions, which we've never done, but I think it's a good idea that we actually stole from some machine learning conference. Thanks to all the speakers in the new researchers sessions, we had 4 for different regions of the world who explained the young members of the community how tenure systems work in different systems. And also thanks to the organizers of the new researchers events. I think this was really nice and many young people participated. So we wanted to give a stage to all these young people, which had a difficult year because they were a little bit pushed aside through all the virtual talks, which were mostly covering the very strong researchers of our community, the well-known people, but not the young people. So I think among the 600, there were many, many, many young people. And to my understanding, the discussions of these live discussions were very helpful for many of them. We also wanted to just give it a try and see what we can do in this year to see if we can develop some new ideas that might outlast after the COVID time. I think we've seen what works well, what does not work so well. There are certainly going to be discussions in the next weeks, what we've learned with this this 1 week of this symposium. I think we've learned a lot and many things work pretty well, in particular this kind of inverted classroom research talks. My personal impression is that this year, 2020, is going to be seen in the future as some start or restart of the digital 21st century. Many things are going to change. Our teaching is going to change in the future. Probably we're going to learn things which are new and work better than we expected before. Conferences are also going to change. And things are going to get more inclusive for everybody and are probably going to be much more eco-friendly in the future. So let's see where all this this travel goes. I think we did our contribution, enjoyed it, but now I think most of us are pretty tired.
Susan and Claudia, do you want to sort of say something?
Can I continue? Okay. So I find it amazing that life is still life. So he has really worked so hard. So let me express my special thanks to all of the organizing committee with Life during Esprea, members Siva Atreya, Andreas Cipriano, Jean-Christophe Morin, and Christian Robert. The idea of a virtual symposium to offer something for the postponed World Congress in Seoul has been born only at the end of April. So our main motivation, as Life said already, was to do something for young researchers who would have little chance to present and discuss their work during this Corona summer. So at that time, because of this cancellation and postponement of basically all conferences, the Bernoulli Society created the position of a virtual event coordinator. And we asked Live to be the first person to hold this position. So I really congratulate us that we did this. So we really had a good, well, had a lot of luck to find him. So we were very lucky. So at that time, end of April, well, we actually joined forces with the IMS. So we often do that, as those of you who have been around for years know this. So Bernoulli Society and IMS are sister societies who do a lot of joint work together. So then we did not think of such a large symposium, or at least I did not. Maybe Live did from the beginning, I don't know. Anyway, so I think Live and his committee have done an incredible amount of work, and this competently and, as he said, very promptly. So the many experimental features of the symposium, as Live mentioned some of them, they have paved the way for future virtual activities. So this first Bernoulli IMS One World Symposium has been an extremely exciting experience for most of us. And it will certainly set standards for future conferences of a similar kind. So, and with these words of thanks, I hand over to Susan.
Thanks, Claudia. It's great to be part of this whole group. I have to say, I've looked at a number of these 10-minute videos, and there's some really good videos. It's great that they're going to be on YouTube. People are going to be able to access them in the future. I highly recommend you check them out. It's just amazing how well people can do these videos. It's very impressive. It's great to see this communication across the world. And my last statement is I want to thank Live for setting the standards for the future.
Yes, maybe Live should show his
plaque.
What,
yeah, Live, show your plaque. Put it close to the camera.
I can read it out. So let me read it out. So the Bernoulli Society for Mathematical Statistics and Probability and the Institute of Mathematical Statistics recognize Live Döring for exceptional creativity and commitment, bringing our community together through the very first Bernoulli IMS One World Symposium. And it's signed by Susan as president of the IMS and by me for the Bernoulli Society. So that is something to last. Yeah, so join me in thanking the team and Live and all the organizers.
Thanks a lot.
Say something?
So everybody have a nice weekend. Bye.
See you. Bye-bye.
I'm heading to the garden if anyone wants to come.
Okay, we can go to the garden for a few minutes. Yeah.
Sorry, where are you going, Andreas? Into the garden? Well, I'm staying in my room up here, but...
Well, you could transport yourself to the garden.
Bye-bye.
There's a thunderstorm just starting here in the Netherlands.
Luckily, not in the garden.
Not in your garden, yeah, no. But
port yourself across, to the garden, the coffee garden.
Your garden?
The coffee
I'm going to
garden.
stay here. What garden?
The coffee garden.
Oh, the coffee garden. Okay, I can go to the coffee garden.
Transport yourself there.
Yeah, I think I could do that.
Second.
Probably. Had some practice. Been a tough week.
Yeah, this has really been a tough week.